All right. So our special guest today, and thank you all for being here today, is Dr. John Nielson-Gammon. He's been on the faculty of Texas A&M since 1991, and he's presently the Regents professor of atmospheric sciences. And he's been this Texas State Climatologist since 2000. And he's written many, many, many articles in technical journals, and the number of awards are the length of my arm, so I'm not going to go through all those, but he's won a number of very prestigious awards. So we're very fortunate to have him today, and his topic's going to be what's changing faster, extreme rainfall intensity, or our ability to determine changes in extreme rainfall intensity. So, Dr. John, are you, well, welcome. You missed my fantastic introduction then, but I'm not, I'll just, everybody had a chance to hear it, Dr. John.
Oh, that's okay. I don't need to hear it. I already know who I am. So anyhow, title of my talk, what's changing faster, extreme rainfall intensity, or our ability to determine changes in rainfall intensity? This is obviously it's an important topic for those of us who are in the Houston area. We're quite familiar with what happened with Hurricane Harvey, which is one of two disasters in the United States that exceeded $100 billion in damages. And the flooding was quite catastrophic, and it went well beyond areas that would normally flood. There was some attention paid to houses that were built within Addicks and Barker reservoirs that flooded, but those were still far enough up, close enough to the top of the reservoir. They weren't expected to flood with a more than 1% chance in any given year, but they certainly did. The reservoir actually filled up completely. So that 1% chance is an important number. That corresponds to something that you might be more familiar with, which is 100-year rainfall amount. Something that has a 1% chance of happening in any given year would be expected to happen on average about once every 100 years. And that's where the 100-year flood or 100-year rainfall amount terminology developed. And for a built environment, for homes and businesses and so forth, there's sort of a bright line drawn at the margin of the 100-year floodplain. Anything within the 100-year floodplain would be expected to flood more frequently than once per century, and anything outside of it less frequently. And if you're inside of it, you've got restrictions on building. If there's something already in there, you've got mandatory flood insurance. Mortgage companies may not take a flyer on a mortgage for something that might not be there in 30 years from now. So it's a critical dividing line. Now that would be nice, and we could work with it as a society if that dividing line were a fixed location in space. But if rainfall intensity increases, that means that the amount of water in any given flood would increase, and that means that the floodplain itself, the area that would flood with a once-in-a-century type flood, becomes larger. Now, there's a lot of factors that influence how big a flood you get. It's not just weather and climate. It's also what's built within the drainage basin, what sort of flood mitigation measures are present, whether you've got a flood control reservoir available, and so forth. All those things tend to be factored into deciding what the 1 in 100 chance is of flooding and where that risk lies in terms of elevation above the stream or the river or so forth. Now, obviously, if the risk of flooding increases, because of climate change or whatever reason, then that means that once in a while, more frequently than one would have expected otherwise, you get a flood that's beyond the 100-year floodplain. You affect properties, you affect people's homes that don't normally get affected by a flood. But as extreme rainfall does increase, you would generally, ideally, like to have the risk of flooding evaluated accurately. And if that gets done, then a home that might have been outside the 100-year floodplain when it was built or purchased could end up inside the 100-year floodplain as the risk of extreme rainfall increases. And if that happens to a homeowner, all of a sudden the cost of flood insurance goes up, the ability to mortgage their house goes down, so they can't take out a second mortgage. You can always sell it, but the person buying it may not be able to take out a mortgage either, so the value of the home goes down. So the problem with this is climate change influences, causes economic losses from extreme rainfall in two ways. One is by increasing the flooding, and you have the things like Hurricane Harvey that have $100 billion cost that happens suddenly, or you have the floodplain expanding, and as society recognizes that risk, you've got economic costs for anybody who used to be outside the floodplain but are suddenly inside of it. So the objective going forward, given that we may be having a change in rainfall intensity, is to understand how big that floodplain might be in the future and make sure that we're putting infrastructure outside of the future floodplain. Doesn't help to put it outside of the past floodplain, because whatever floods might have happened in the past have already happened. What we care about is mitigating risk for the future. And if the future is changing, we have to take that into account. Now, how do we tell how much extreme rainfall is changing? Well, probably the most straightforward approach would be to look at the data. We've had observations of daily rainfall going back more than 100 years across the entire United States. We can plot the data at any given location and analyze the trend with that. You can analyze the trend in stream flow, trend in floods, and that's sort of the standard approach for hydrologists who've got to deal with all sorts of things that might happen in a river basin, including increased construction, flood control, a freeway that suddenly blocks part of the flow during a flood, that sort of thing. They spend a lot of time looking to see whether the history of flooding is something that hasn't really had a risk change over time, or whether the risk actually has changed for some reason or another. Now, climatologists don't really, well, you can follow that approach if you want to. It's a simple way of doing things, but it can be very misleading. Give you one example of that. I mentioned Hurricane Harvey. That's a big data point in the flood record. And so if you analyze the trend in heavy rainfall in the Houston area, you're almost guaranteed to get an upward trend just because you've got this one massive event near the end of the time series, very recent event. Whereas if you did the same sort of thing for Victoria or Corpus Christi or someplace that didn't get Hurricane Harvey, you don't have that event that guarantees an upward trend. Trend there, those other places could be up, could be down. It depends upon whether they happen to have those big events near the beginning of their record or near the end. And sure, the odds may be increasing, but that doesn't mean that something actually happened at that time. If you've ever gone to Las Vegas or played the roulette wheel and bet money on a number, you know that the odds are 1 in 36 or 1 in 38 because it favors the house. So your number is going to come out, but that doesn't mean that if you bet 38 times, you'll come out even. You might win big, you might lose everything. So what we care about for trends to figuring out what might happen in the future is not what actually happened in the past and how that changed. What we care about is how much the risk of things happening changed. And that's, I think, an important distinction. You want to know how your risk has changed, and whether or not your number came up recently. That gives you some information on whether the odds have changed, but it's not very determinative, as you can tell between the difference between Houston and Victoria. Probably Hurricane Harvey could have stalled over Victoria just as easily as stalled over Houston, and you get a very different trend in extreme rainfall in Victoria, and you get a very different trend in extreme rainfall in Houston. But climate change has changed the risk of extreme rainfall by about the same amount in both cases. You can't figure that out just from the data. So what other choice do we have? Well, looking at the historical trend is one bit of evidence. There's two other techniques that we use. One of them is looking at climate model projections and historical simulations. The models aren't the real world, but they're similar to the real world. If they show a trend similar to what's actually happened, then that's an agreement between model observations to give you confidence that both of those are manifestations of climate change effects. And the third technique is physics, our understanding of how the climate system works. If it's obvious from physical principles that climate change ought to be changing a certain aspect of extreme weather in a certain way, we can have more confidence in a historical trend that shows that versus a case where we don't really have a clue what climate change would be doing. So let's turn to how we might analyze the observations themselves. The challenge, for looking at something like the change in average temperatures, it's actually fairly easy because you've got, for daily average temperature, you've got 365 observations or so every year. And you've got 100 years worth of data, that's 36,000 observations. For extreme rainfall, we are focusing on the very tail of the events, the very heavy events. And typically what you do is something like look at the heaviest rainfall event in every year and look at how those are changing over time. So instead of having 365 data points per year, you have one data point per year. So automatically you're being affected by statistical noise to a much greater extent. And then it's harder to analyze a trend than it is to analyze sort of an average. For example, suppose you wanted to estimate the average of temperature in Houston. If you have one data point, you can make an average estimate. You can say, well, that's all we know. That's a plausible guess for the average. You have two data points, you can probably be a bit more confident in your estimate by averaging those together. Suppose you wanted to estimate the standard deviation, how much variation there is in temperature. With one data point, you don't have any information whatsoever on that. With two, you got a little bit of information. Okay, that helps a bit. But the farther along you go in estimating statistics, the more data it takes. To estimate a trend in extreme weather, you need to know the trend in the average extreme. You know how much variation there is in the extreme. You need to know whether the extremes are skewed to one side or the other. You need to know whether the average is changing over time. You need to know whether the spread is changing over time, which of course translates into whether the rate of change of extremes depends on how extreme the event is in the first place. And we actually expect that to be the case for extreme rainfall. The more extreme the rainfall, the greater the impact of climate change. So we've done that sort of analysis. We've done it for South Central and Southeast United States. And what we see is basically an increase in extreme rainfall by somewhere around, well, the 90% confidence interval is about an increase of 3% to 20% per degree of global warming. So definitely not zero, or almost certainly not zero. And the trend also is consistent with what we know physically about climate change, which is that a warmer atmosphere can hold more water vapor. And so if it's raining, there's a lot more water that can be coming down from the sky. We call that effect a thermodynamic effect. That's a complicated word that if you're a college student, you hate the concept entirely. It basically just means what follows directly from knowing temperatures go up, right? So higher temperatures mean more hot extremes and fewer cold extremes, all else being equal. And it also means more extreme rainfall, given that a hotter atmosphere can hold more water vapor. That's one of the two ways that climate change affects extreme weather, this direct effect on things like temperature and extreme rainfall. The other way climate change affects extreme rainfall is through what we call dynamics, which can include changes in the weather patterns or changes in weather systems themselves. Like if hurricanes become stronger because of climate change, then that could lead to a change in rainfall from hurricanes. If hurricanes follow different tracks than they used to because of climate change, then that means extreme rainfall in some places will increase and some places will decrease. As a general rule, physics can tell us a lot about the thermodynamic effect, but it doesn't tell us hardly anything about the dynamic effect. For that, we would have to rely on the other evidence, either from climate models or from the observations. But climate models say that for the United States, probably the most important effect is that thermodynamic effect, the direct effect of temperatures. And if that was the only thing happening, we would expect an increase of extreme rainfall of about 7% per degree, which fits within that 3 to 20% range that we find from observations. So extreme rainfall definitely increasing. Maybe dynamics is amplifying it even more than just the temperature effect by itself. Now, I alluded to the effect of evidence from models, but models are kind of tricky for a lot of types of extreme weather, including heavy rainfall, because they can simulate heavy rainfall, but they're simulating it on a scale of, let's see, something like 500 square miles, as if that's the size of a thunderstorm or something. And well, if extreme rainfall increases on that scale, it probably increases on a smaller scale also. So it gives us confidence in the trend direction, but we might expect that the amount of rainfall occurring over 500 square miles might change at a different rate than the amount occurring over 1 or 2 square miles. Who knows? The models can't tell us that. So our evidence for extreme rainfall increasing, we've got good scientific evidence that it ought to because of the higher temperatures. We've got good observational evidence that it ought to because of the trend we see in extreme rainfall. And we've got okay computer model evidence that it ought to be increasing also because it increases at least on the scale that the climate models can simulate. So all of that points to the fact that we're going to have to deal with increasing risk of extreme rainfall, increasing size of floodplains, and so forth. So last bit I want to talk about is what we're doing about it. The we is a collective we. It includes me. It includes a lot of other people. It also includes Congress, which a couple of years ago, before it became totally dysfunctional, passed a law that said that the federal government, when it estimates the risk of extreme rainfall, has to take into account trends in extreme rainfall. And they also have to do this analysis for the whole United States. And they have to update it every decade to keep up with the changing climate. So that effort on a national basis is ongoing. They expect to have sort of the results of a pilot project available in the spring for scientific comment and public review. They expect to have phase one done for the whole United States about a year after that, and then phase two done a year after that. Phase one would be analyzing the historical trends and including that information to estimate the present day risk. Usually, of course, if you have an upward trend, that means that your estimate of risk increases in the present day. So we're expecting there might be some consequences just from that update because the floodplain changes and so forth, and then the risk that people perceive changes, the risk that insurance companies perceive changes, and so forth. Second phase of what they're doing will be looking at climate models and looking at projections to get estimates of the future change, extreme rainfall. So that's fine. That's a vast improvement over what has been done. But I think that particular method can be improved also. And we're actually going to be working on that and are working on it for the state of Texas. Texas Water Development Board has contracted with us at A&M and also at Rice University to come up with estimates of extreme rainfall risk that take climate change into account. They didn't actually use the words climate change, but changing weather patterns and so forth, that's what it implies. And the main improvement we want to make over what the federal government's planning on doing is to combine the information from historic observations and from climate models. Right? We got climate models are one way of estimating the trend, and observations are a second way of estimating the trend. But if you just had information from the historic trend without climate models, you can extrapolate that trend into the future and make a guess as to what might happen. So the historic past gives you information about the future. Conversely, the climate models, which are projecting these trends of extreme rainfall, give you information about what probably happened historically. That doesn't include contamination from things like Hurricane Harvey hitting one place and not another place. So the climate models help constrain the historic trends, and the historic trends help constrain what might happen in the future based upon the extent to which they're compatible with the climate models. So what we're doing, and we hope to get it done fast enough to affect what happens nationally, is to combine the information from the historic trends and the climate models into a consistent overall estimate of the impact of climate change and extreme rainfall across the entire state of Texas. We're scheduled to be wrapping up that project early next year. We'll have some preliminary results to present at a couple of conferences around New Year's, so stay tuned on that. Hopefully, we'll have some very valuable information for the state of Texas on what's happening with extreme rainfall in these parts. So that's what we're working on. That's what I wanted to share with you right now. I'll be happy to answer questions.
Great. Thanks for that. So we've got a number of people with their hands raised already. So we've got a few questions for you. First, Bob Jones.
Yeah, good afternoon. Thanks so much for the discussion. So I didn't know about this government study that you referred to, but I just kind of wonder, what data are the insurance companies using? It seems like they're a little bit ahead of other studies as they assess risk, whether it's Florida, Texas, or even in Europe. So, are we behind in studies as compared to what the insurance companies already know?
Generally speaking, yes. They have a much more immediate economic incentive to stay on top of things because they can make money by properly pricing insurance policies. And even beyond that, insurance companies package their policies and sell them in bulk to what are called reinsurance companies, which are responsible for dealing with very large scale risk, and they're definitely on the ball with this sort of thing. So the problem societally with that is that there's economic incentive for insurance companies to keep all of their information and analyses as private as possible, because that's how they can make their money. That gives a competitive advantage over other insurance companies. So we're stuck with this segment of society that puts a lot of money into estimating these changes in risk, but doesn't want to tell anybody about it.
I hadn't thought about that. Thank you.
Sure. Our next question comes from Stuart. Stuart, you're muted.
There we go. How's that?
Yep.
Okay. I wanted to thank you. And my question is kind of the flip side of the coin. Drought. That increased precipitation means that water is being evaporated from somewhere and being transported by these low pressure systems and dumped someplace else. So do you have any models about drought and increased length and duration of drought systems?
Yes, I do. That's a whole other talk. It's not purely the flip side, because let's see. In a sense, if extreme rainfall is increasing, then you get more periods of time between the extreme rainfall. So that would be expected to lead to an increase in the frequency of drought if it's happening relying on time scale. Also, increased temperatures themselves lead to greater evaporation rates because the amount of moisture in the atmosphere can't keep up with the increased temperatures. So even if overall rainfall amounts don't change, models are very clear that the amount of moisture in the ground, the amount of soil moisture available to plants and so forth and able to recharge aquifers is going to decrease everywhere in the United States, basically. Now, there's different kinds of drought, so that's the part that affects agriculture. That's the part that affects aquifers. A lot of places in Texas and elsewhere get their water from surface water, from reservoirs. And there you got an interesting, I won't be taking 25 minutes for this answer. I'll get to the end pretty quick. There you've got two things going on. You got the increased intensity of rainfall ought to lead to more runoff, but if the soil moisture is lower, that ought to lead to more water soaking into the soil and thus running off. So it's not obvious which one of those factors would win out. So relying on climate models, what we see happening and projected by the models is that a dry month, the amount of runoff decreases. In a normal month, the amount of runoff decreases a great deal. And in a very wet month, the amount of runoff increases. Now, total runoff is dominated by the amount you get in these very wet months. So if you just look at a trend in runoff, that looks like it might be increasing. But if you look at the details, what it comes down to is you can't count on as much runoff from month to month replenishing the reservoir, but every once in a while you're going to get a big flood, which might mean you have to leave more space in your reservoir to take into account that flood. So unfortunately, that's not a good combination for water supply. You got less reliable inflows and you have to worry about flooding more. So that means that that type of drought probably gets worse because of climate change also. And you know, the drought we had in most of Texas during 2023 is sort of the type of drought we expect in the future, where drought impacts come on fairly rapidly because of the high temperatures. And doesn't mean we have necessarily less rain than we had in previous droughts, but the system dries out faster.
Thank you.
Thank you. Larry Howe.
Hi, yeah, so thanks. If I heard your comment early on in the talk, you were using an example of like the 100-year floodplain or the flood risk areas. And my question was kind of, how often are those flood risk areas updated? And do you have a feel for how often that flows through the insurance rates? And the reason I was asking kind of is, you know, as we're getting better at predicting how the climate impacts may affect, for example, 100-year flood risk, what's the lag before people start feeling that in their pocketbooks?
Okay. There's a couple different things going on with that. First off, there's the official floodplain, which involves floodplain is supposed to be located officially. And as you might imagine, for anything government-like, involves a long process of vetting and so forth. So it's like several years after the new estimate of 100-year rainfall amount comes out, the official estimate of 100-year floodplain comes out. And 100-year rainfall estimates typically only get updated every few decades. As I mentioned, we're going to improve on that, so that part will become more frequent. But at the same time, there are more unofficial estimates coming out. For example, the First Street Foundation recently did a big publicity splash about how much how the 100-year floodplain is changing and by what percentage and so forth. And that was based on their own hydrologic modeling, combined with just focusing on the last like 15 or 20 years or so of historical records, and using that as an estimate of the current climate conditions. Now, I don't like that approach because 20 years is much too short to robustly estimate extremes, but it did sort of get people's attention. In the future, we'll probably also have widespread access to floodplain estimates from machine learning algorithms. So everybody will be able to say, okay, what's my current risk of flooding at this location right now? And if rainfall increased intensity by 10%, how much would that risk change at my location? Probably going to be like maybe a decade or so before that sort of information gets into people's hands and they're able to work with it. But that'll I think revolutionize how people perceive flood risk, and it'll change the real estate market as a result.
Okay, thank you.
Joe Garfunkel.
Hi, Dr. John. Thank you for your presentation this afternoon. My question, I'm very curious about your role as the Texas State Climatologist and what kinds of interactions you have with the Texas State Legislature. What information are you sharing? What kind of reactions are you getting from them?
Well, with the legislature, I typically would be giving be asked to give testimony maybe once or twice a legislative session. I might get asked to provide input on a bill that would involve climate change or maybe involve my office. So that sort of thing. I don't go out and lobby the legislature for anything, because my role as state climatologist is to not advocate for political stuff, but to be a reliable source of information for everybody. So that's the level of interaction I have with the legislature. They have shown a lot of movement recently regarding climate change. I think Hurricane Harvey sort of kicked people into recognizing they had to deal with risks associated with climate change, even if they didn't necessarily call them that. So the legislature required that ERCOT and the PUC and so forth take into account my forecasts of cold weather risk and heat risk in their rulemaking process for grid resiliency. And they required the Water Development Board take my information into account for flood risks, which is part of why they contracted with me to do the analysis. So they're calling on the state of Texas to pay more attention to me and, as a result, more attention to climate change.
Thank you. If I can just ask a quick follow-up question. I heard you mention about ERCOT. And with the heat data that you're feeding to them, do you know whether they're actually including that in their modeling? All of the stress on the grid this summer, it seems like they still have a lot of work to do.
Yeah, they chose to take a minimalist approach with respect to me, in the sense of, they had their own meteorologist on staff that's forecasting loads and so forth. And so they had a certain degree of trust with that person. They had them analyze the long-term trends. And I had a look at the results, and they did a good job with that, I think. So no major complaints there other than feeling left out. But they also talked to me at the beginning of the summer about the outlook for the summer, and I don't remember exactly what I told them, but they said, "Boy, that was useful." And I had a much bigger conference call with them last month to talk about what the outlook was for the winter. So, yeah, climate is getting their attention, and they're at least looking toward my office to help them out in that regard.
That's great. Thank you.
Okay, next in line is Linda. You unmute yourself.
Well, what I'm thinking about is that, when the fronts collide like they're doing now over Texas, because the warming Arctic, we can get even more really cold spells from the warming Arctic because of the instability, and then the warm Gulf. And so when these meet, we get extreme rain, it seems. So I'm just wondering if there's any modeling or any way to start evaluating the strength of these fronts as the tropics, well, I guess, let me see, the Arctic will be warming, so the tropics, I guess, will still be warm. So as the fronts collide, any measurements can be taken about that currently? Is that clear?
I haven't seen it. I haven't seen any studies looking specifically at changing the strength of fronts. That would be a fun thing to do. I think that because the Arctic is warming faster than the tropics are, that the average strength of fronts is probably decreasing. That doesn't mean the consequences of fronts are decreasing, because you've got more water vapor that's being forced upward along the front, so you get more intense precipitation, and changes in wind patterns could lead to changes in severe weather also. But the front itself is probably on average a little bit weaker than it used to be.
Okay, thank you.
Next, Wakar.
Thanks, Roger. So my question, it goes back to the extreme rainfall statistics that you raised in a very interesting discussion at the beginning. And I was just taking a quick look at the IPCC's AR6 report from a couple of years ago. They show heavy precipitation over land for a 10-year event. It would be, for every degree Celsius, 7% wetter, which is exactly 6.7, exactly in line with what you mentioned based on thermodynamic effects. And it also says that the likelihood would increase 1.3 times. And I'm just thinking that that's a 10-year event they're talking about. if you consider a 100-year event, the likelihood of that probably increases more than 1.3 times. And those are the kinds of events that are really problematic and would affect the floodplain a lot, I'm thinking. So, the extreme events would be even more likely to occur. So I'm thinking the floodplains would be affected quite a bit by climate change. So just any reaction to that?
Yeah, I think you're exactly right about that. So, I mentioned the increase. You can look at increases in extreme rainfall in terms of an increase in amount or an increase in odds. It's sort of the opposite sides of the same coin. You can't have one without the other. And for a given percent increase in intensity, the odds go up faster as you get toward more extreme events. So with Hurricane Harvey, there was a study that looked, a lot of studies with Harvey, some are better than others. The one I liked the best looked both at observations and climate models and concluded that essentially the odds of heavy rainfall like Harvey produced increased by a factor of 3 over the past century plus. So, yeah, the rarer events, they stay rarer, but the odds increase faster than the odds of the more run-of-the-mill events do.
Yeah, that's it.
To take that to extreme, you have an event that couldn't have happened without climate change. The odds of that event have increased by an infinite amount.
Yeah, that's true. Thank you.
Okay, next would be Glenn. You need to unmute yourself, Glenn.
My question's somewhat related to just what I was just asked, but when we define, if I try to define an extreme event to the general public, they're going to generally want to know some numbers or some better way to define that. Can you give me a better way when I'm talking to the public, people that maybe don't have a whole lot of knowledge about climatology? What would be the best way to define extreme? Because it's not only the amount of rain, but it's also the amount of rain occurring over a short period of time that has the impact.
Yeah, I mean, even the word extreme sort of has two different meanings. We talk about extreme weather in terms of events that occur very rarely, in such a way as they have important impact. And then we also have extreme weather as things that are automatically extreme, like a hurricane or tornado is extreme weather, even though tornadoes are fairly common across the United States. Each one of them is an example of extreme weather. There's no, for the first case where you've got something happening that's at the extreme end of the distribution, there really is no set cutoff for it. It could be a 1 in 10-year event, it could be a 1 in 100-year event, or it could be whatever causes whatever. I guess perhaps the best way of describing it might be, broadly speaking, it's the magnitude of the event that would exceed the design limitations of whatever aspect of society you're dealing with. So for 100-year, for flooding, 100-year event is the most common sort of thing for impact. 10-year event would fill a storm drain. And the farther out you go, the more extreme, the bigger the impacts, the more things fail as a consequence. Not a very good answer, but that's because we don't have a very good answer.
I'm just trying to figure out how to talk to the public about it, but it sounds like a 1 in 100 year is a key, I guess, extreme, probably the best definition of extreme for the public. Another question quickly is the jet stream is changing. Can you talk a little bit about that and the impact it's going to have?
I can talk a little bit about it. So generally speaking, the jet stream itself is probably moving a little bit farther north than it used to. And then also there's changes in the waves in the jet stream, the ridges and troughs that lead to cold air outbreaks and heat waves. And science on that latter aspect is not very well settled yet. It makes sense that as you get the climate system changing, some wave patterns become more favored and some become less favored. That can mean that some places end up with getting locked into certain weather patterns longer than they used to in certain seasons. There's been talk about maybe heat waves becoming more long lasting because of that factor in the northern hemisphere. And there was some research recently that talked about colder outbreaks possibly becoming more frequent. Although, those are all what we call dynamic effects. And even if you get colder outbreaks more frequently, it doesn't necessarily mean your risk of cold is increased, because our cold air is coming from the Arctic, which is warmer than it used to be. So it's challenging to sort all that out, but that's the sort of things that changes in the jet stream are thought to implicate.
Okay, thank you. Appreciate your effort. Thank you.
Larry Lindenschmidt.
Great. Thank you for spending part of your Saturday afternoon with us, Dr. John. That's above and beyond the call of duty. I testify frequently before Texas legislative committees, and I was very surprised to hear that they contact you, because when I bring up climate change, there seems to be no interest. The legislators that are trying to get the state of Texas to establish a climate change plan can't get their bills heard. When I talked to the people at the Texas Water Development Board, they said they couldn't use the words climate change, as you somewhat alluded to, but at least they're dealing with it. So I'm just curious, as I testify, or as we're working to have impact at the Capitol, am I missing something, that they're paying more attention to you than they let on about? Or how do I help, and how do we help to make climate change more visible and acted on by the Texas legislators?
Well, I think that in general, private views of climate change, especially among Republicans, legislators, is going to be somewhat different than their public views on average. But of course, what they pass will reflect and partly define their public views. That doesn't necessarily help you that much. I think the problem with, say, a climate action plan and so forth is that those threaten to be, they're non-specific, complicated policy changes that are going to be expensive, and it's not obvious necessarily what benefit it'll have, especially in the short term. If you can break it down into the individual bits and pieces, it becomes a lot more palatable. So if you say, well, we need to take into account climate change and figuring out what our risk is for cold air bringing down the power grid, that's something that the legislature has already spoken on and said, even though we won't say it's climate change, yeah, we have to deal with that. So it may be, as these things accumulate, it'll be possible to get to the point of saying, okay, well, look at how we're dealing with climate change in all these different ways independently. We ought to do it in a more comprehensive fashion. But until we get to that point, I think there's still a lot of progress to be made in dealing with it in bits and pieces.
Okay. Yeah, but it seems that if it was fully thought through, we'd be thinking about it and how we build our roads, because of the buckling that occurred in Houston is a prime example. We'd be thinking about it in terms of insurance markets. They're more focused on getting companies out of here that use ESG in their system than they are on bringing more insurance companies in, and which is a concern. Everything about water planning needs to take it into account, and you're talking about the grid. So it it seems like then you're saying just take each piece that we can and speak to that and hope that somewhere down the road it becomes more comprehensive. Is that a fair restatement?
That's what I think would be most effective for the goals you're talking about, given where we are right now in terms of the political mood in the legislature. Yeah.
Okay. Do you have adequate funding in your operation in your office to do the work that you'd like to do?
No.
Okay.
I don't get any money from the legislature. I get occasional money from state agencies for special projects, such as the one I'm doing for the Water Development Board. My base funding comes from University Texas A&M University itself, but situation's improving in a sense. We're right now actually pursuing an initiative to get federal funding for all state climate offices. Initial works in that, and hopefully that'll bear some fruit next year, if not the year after.
Thank you. I just want you to know you're appreciated no matter what the legislature, the governor does or does or don't does or do. So thank you. Thank you very much.
All right, thank you. Sure.
Well, we're running short on time. Dr. John, do you have a few more minutes if we keep going with a few questions?
Yeah, I can hang on a little bit. Sure.
Okay, we'll try to keep it short. As moderator here, I actually like to follow up with a insurance question. Seems to me the way I understand insurance works is that if you want a rate increase, that has to go through like the state legislature, some state board to get approved for that. And because of climate change and fires and floods, et cetera, hurricanes, sometimes these insurance companies want to really jack their rates up, and then if they're not allowed to do that, then they leave the market, right? For individual states, which I guess is happening in California and Florida and maybe Texas to some degree. If they want to get an increase, and you say they don't have to share their data, or to get the increase, they can share their data so that they can justify increases, because every time I hear about an increase, they're always saying, oh, it's the cost of materials. They rarely say what's really going on, for particularly Florida, it's climate change. So I'm just kind of curious how the whole approval process to raise rates, because they just can't unilaterally raise their own rates, correct?
Yeah, I don't know how the situation works in Texas, but yeah, in California, it all has to go through a agency or board that was tasked with approving it, and they had implemented a rule that the increase can only be such percent per year, and wildfires are increasing at much more than that percentage per year, and so it was becoming less and less profitable to actually write insurance policies. Like I say, I don't know what the rule is in Texas, but it's an interesting proposition that one might say that requests for greater rate increases require greater amounts of data being released at the same time.
Okay. I'm going to say a couple more questions. Let me see if everybody's had a chance to. I'm going to go to Susan because you haven't had a chance yet.
Yeah, I just kind of related to what Larry said. Are you connected to the climate caucus in the legislature in Texas legislature? Because if not, it would be great to have you connected. And I wondered if we could, facilitate that or something, because of course we're already thinking about the next legislative session, and if we can get some more movement. So yeah, if you can say something about that and any connections, or if you want any connections or whatever about the climate for the legislature.
Yeah, they reached out to me and invited me to give a presentation at the monthly virtual meeting. A few months back, I focused on the risk of extreme cold and extreme rainfall, and I know their parting words were, "Well, we need to hear from you more often," but I don't know whether that will pan out or not. But yeah, you would think that the Climate Caucus would be in close touch with the state climatologist, but so far they haven't really been that.
Yeah, it may be that they don't know you or you don't know, I don't know, but I mean, sometimes it's just somebody calling the meeting is what's important. And, so that's what I'm wondering. And really, if there is something, in conversation, we find that now's the time to start thinking about bills for the next session, that we should consider. So I'm sure your wisdom would be useful in helping decide to find that. So anyway, I'll leave it. And if it's something that we facilitate, let us know.
Okay, thank you.
Okay, thank you.
What I think I'm going to propose now is just I think we've had the time to talk with Dr. John Nielson-Gammon, and I think we need to honor his time, our time commitment to him. So I'm going to pass on any more questions at this point. But what I would like to do is just kind of go through what's coming up. And to do that, I'm just going to show real quick. So first, we want to give thanks to Dr. John. You can unmute yourself and just maybe get a round of applause for him.
Yay, thank you, thank you.
Yeah, thank you.
Thank you.
Great presentation.
Thank you.
Keep up the good work.
Yeah, we really thank you. Thank you so
You're
much.
welcome.
And we're going to have one more meeting before the end of the year. I'm going to the December and November meetings are going to be combined because they kind of fall towards the holidays. So we're going to have the next one on Saturday, December 2nd. It's going to be our own Larry Howe. And speaking of the legislature, he's going to talk or kind of give us a review of the Texas 2023 legislative session. I hope that's accurate, Larry. Is it?
I'm just gonna put it on my calendar right now.
I did clear this with you first, but hopefully you remember that you were.
Yeah, no, thanks for the invitation. Appreciate it.
Yeah, this is going to be great. So anyway, I really want to thank everybody for being here. I thought it was a great session. We had for Dr. John's benefit, I think we had over 25 people. This is a really impressive turnout.
We had over 30 actually.
There were
35 was the max I counted.
Wow, that's really good. So I want to thank him for just a really tremendous kind of I learned a lot. It's one of those things is like drinking through a fire hose. There's so much useful information. So until December 2nd, we will talk with you later.
Thank you, Roger.
Thanks, everyone. Bye.